Now let's turn our attention to the stability and condition of a mathematical problem. The condition of a mathematical problem relates to its sensitivity to the change in its input parameters. And we generally say that a computation is numerically unstable if the uncertainty of the input values is grossly magnified by the numerical method. We can explore this again with the first order Taylor series expansion, that is f of x equal to the approximation of x at our point x tilde plus the derivative x tilde minus multiplied by the difference in x. And we can also look at the relative error of f of x, that is f of x minus our approximation divided by f of x. This, of course, can be approximated as f prime x tilde You can do this through the first order Taylor series expansion. We also know that there is an error in x, so the relative error of x is the difference divided by our estimation. Now if we take the ratio of these two numbers, we call this the condition number. And that is a measure of the extent to which the uncertainty in x is magnified by f of x. So in other words, the condition number is equivalent to, as I said, the ratio between the two numbers. You can do this calculation if you want. It is equal to x tilde multiplied by f prime divided by our approximation. Make sure you know how this number is configured. What is the ratio between which relative error is in the denominator and which is in the numerator. But now we can explore this quantitatively by saying that if the condition number is greater than 1, so if the condition number is greater than 1, then our relative error is amplified, whereas if it is less than 1, the error is attenuated. And if the condition number is very large, we refer to that function as being ill-conditioned. So let's explore this again with another example.